Mic test, mic test. Hello, we are Group 1202, and this is a recollection based on the past 7 months of work on the research topic of design and manufacturing of Auxetic materials through 3D printing. Learning points upon this journey have been numerous, and so we are dividing them into two major portions: the theoretical knowledge that we gain, as well as the technical expertise that we gain. Now, theoretical knowledge constitutes as one of the major learning points in our project, as we had to come to understand the nature of Auxetic materials and its benefits. Before anything, we must introduce the core concept of the Poisson's ratio, which, as you can see, can be defined by the negative value of the lateral strain divided by the axial strain of the subject when subject to force. Good. Now let's take a look at conventional materials, which both have conventional or even no basic cellular structure. These materials have a positive Poisson's ratio, and as can be seen in both diagrams here, if we were to compress or stretch these two cylinder boxes, we would arrive at results which would show an inverse relationship between the transverse and longitudinal strain. Moving on, here are some materials with a negative Poisson's ratio, which are your Auxetic materials. As opposed to the previous diagrams, if we were to compress or stretch these two similar boxes, we will see a direct relationship between the transverse and longitudinal strain. Fascinating, isn't it? This relationship between strains is the defining feature of Auxetic materials. Put simply, they become bigger when stretched and smaller when compressed. This is due to the special designs of the basic cells in the materials, which their highly unique and specialized rib designs help achieve different degrees of Auxetic nature, for it is the movement of the ribs in the structures under pressure that produce the Auxetic effect. In simpler designs, when force is applied, a buckling effect is seen in the ribs, highlighted in the drawing, or vice versa. Unlike conventional materials thus, they can hence achieve a negative Poisson's ratio as illustrated in the drawing, whereby the stretching of the Auxetic structure instead allows the material to increase in area. Now by this time, you might be thinking, so what exactly is the use of Auxetic materials? What does the negative Poisson's ratio entail? Among some of the benefits of using Auxetic materials, one of the most prominent is the incredible improvement in indentation and fracture resistance, opening up to new worlds in medical and military fields. These were important learning points, as it is from this basis that we are able to proceed into our problem identification, where we realize that the Poisson's ratio of these structures can be heavily optimized to provide standing data and serve as foundation for future research. Another aspect of our learning points are from the technical aspects of making such designs, which we shall present in terms of problems faced and how we had to solve these problems, and hence in the process serving as a learning point for us. The problem that we first had to solve was finding the Auxetic cellular rib designs. Due to the special nature of Auxetic materials, emphasis had to be placed on the rib designs, and this was a major challenge because most research used the process of guess and check to find these designs. However, we found a systematic approach used to find possible cellular designs that had negative Poisson's ratios, with credit to a research paper which went extremely in-depth to predict parameters and possible structures using a systematic approach towards formulating such structures. Its name is Formulating Basic Eigenmode Auxetic Cellular Design. Symmetry is very important in all cellular designs, and hence, by using basic eigenmode, the vibrational modes of an oscillating system, we aim to preserve this. Basically, eigenmodes of periodic boundary conditions with basic cellular structures usually have a negative Poisson's ratio. The application Abacus 6.13 thus subjected 3 lattices, basic cellular designs, to eigenmode analysis, and designs A, B, and C were used. For the periodic boundary conditions, these were the conditions that were used to determine the eigenmodes of cellular designs. Thus, basically, the eigenmodes that were subject to the virtual stress test filtered out those with negative Poisson's ratio. These are the eigenmodes of the 3 basic cellular lattices that we have seen just now. And these are the eigenmodes filtered out that have negative Poisson's ratios. As you can see, their Poisson ratio is calculated above. This hence served as a very important learning point for us, as it gave us the basis of understanding for the exploration of possible eigenmode structures with confidence that the designs which are produced do indeed produce this Auxetic effect. We could hence find more designs on our own if the occasion called for it, and allowed us to learn the importance of research too. The next step of our project then was to translate the theoretical designs into reality, into 3D designs. We used SolidWorks, a professional designing program, to get the job done. However, at the start, due to our inexperience, we made sluggish progress. We went in the direction of making the unit cell as you can see, and cut extrude into leading to a design like this. However, this was the wrong method, as this made it extremely difficult for us to adjust variables and change factors to find the optimum settings. Our solution required us to change the way we view an in-unit cell, which was the problem. The unit cell actually lay at a rib, not as an individual shape, and with that change in mind, we went on to this. Looking better? Our learning point here stems from a new understanding of Auxetic materials, as we learned the importance of these rib designs, which are integral to the Auxetic nature, as I explained earlier. Then came our second problem. We created our designs by connecting all the ribs and used primitive methods in joining the different sections and rows together. However, this meant that the resolved extrusion could only recognize one spline. This hence served as a learning point, because we only became aware that in SolidWorks, it was impossible to extrude multiple surfaces of the same spline at the same time due to parameters set. We realized that our method exhausted unnecessary time, for when ultimately we could have just used a much simpler method which we found through exploration. This taught us the value of proper planning and exploration before execution in order to save time. In the end, using the linear pattern function, we managed to extrude properly, finally into these. Finally, we had to actualize our designs by using 3D printing right after we were done refining our designs according to the requirements of our mentor, which we then sent in our job for printing. Unfortunately, due to the overloading of samples in the job, the 3D printer broke down after we printed our second batch of samples. Furthermore, we had to discard certain samples with defects due to the overloading of samples once again, and conduct compression tests with what we had left. We also had to go through the exhaustive process of manually cleaning our samples. This was an important learning point, as it was the first time we witnessed the actual process of 3D printing firsthand. Once that was done, we were given the green light for compression testing. Now, compression testing takes a pretty long time, roughly 30 minutes per sample, and coupled with the fact that we could only go once a week as the other days were booked by NTU students, we had to visit the lab several times over several weeks for us to finish collecting the data on all our tested samples. During the testing, we identified certain physical problems with our samples which stemmed from, once again, the overloading of the printer as well as the very design itself, which we then consulted lab manager at the compression lab for advice and resolved these problems. We then realized that 3D printing should be done with suitable spacing between samples and in more batches than we did, for if not, our specimens would be uneven with unwanted defects. Also, we learned the importance of symmetry in our designs when we send the samples for compression testing, as asymmetry would result in uneven compression at the compressed surface. And of course, we learned that we should never try to speed up the compression testing process through the hard way of having to salvage broken pieces and cleaning up the lab floor.
Since our conception, especially into our research of
So,
materials.
what made this project so special?
Well, this project is really special to me. Especially, I think one of the most important reasons was that in all my 4 years in high school, I've never done a project whereby I delved into research in a scientific field that is actually very sparse and very advanced in the technical aspects. Because Auxetic materials and this kind of designs is relatively advanced in these research fields due to the fact that it's newly discovered, and despite its limitless possibilities, there are a lot of hindrances to it, such as a lack of optimization of designs. Hence, our project actually felt very special to me, because even though we face a lot of challenges facing this kind of problems, the fact that not a lot of people actually delve into research and things like that. This aspect, we actually learned a lot, and we made very sizable contributions to the scientific community that I believe can be of use to researchers in the future. We actually learned a lot of learning points throughout this journey, and I think the most important learning point has to be that of time management. You see, one of our major challenges since the start of the year was that our group, our IS group, and our external mentors all have very largely conflicting timetables and schedules. Our external mentor, who is from NUS, she herself is pursuing a PhD degree currently, and that means that she is very busy and has not a lot of time to devote to IS group like us. So we have to make sure that the times that we meet together was essential and very effective to ensure that we maximize efficiency and we can make progress despite the short amount of time that we can actually consult her. So one of our plans that we devised was that before each meeting with the NTU, we actually had this very important point whereby all 4 members of us, or whoever is going, will actually meet up and prepare beforehand. We will discuss thoroughly about what we want to achieve during that NTU meeting and what we felt that should be done during that. Hence, when we actually meet our external mentor, we have a very clear goal in mind about what we actually want. Research was a very integral part of our project because it also constitutes as one of our early mistakes. At the very start of our project, right, we did not actually want to understand the nature of Auxetics because we felt that the technical aspects and the mechanical background, the knowledge background that is required actually far exceeds us as secondary students. Hence, we were not willing to delve into this field, and we felt that maybe it was okay if we actually simply just do the designs that were given to us by external mentors. After all, right, the external, the knowledge based and technical based things, right, can be just left to an external mentor, or that's what we so thought. Hence, what happened was that we were at the start, right, we were actually creating a lot of designs that did not actually fulfill any purpose at all. We wasted a lot of time because of these mistakes. For example, how we actually identify our cellular base, the cell itself, the basic cell itself wrongly, which resulted us in creating a lot of designs, but ultimately realizing that it cannot be printed out because it was a faulty design in itself. Hence, it was a very important learning point as well. Also very important was the fact that our external mentor did not want to spoon-feed us. It was a very important and correct decision on her part, because if not for that, we would not have been able to understand and learn as much as we could have from the IS project. We actually had to do a lot of research ourselves, read papers, actually find books. There were not a lot of books in libraries, hence we actually had to make so-called excursions to different libraries around Singapore which had this 1 or 2 special books about Auxetic materials, and sometimes we even had to borrow an entire book simply just to find that one chapter about Auxetic materials that we wanted. Hence, we made a lot of this research, we read a lot of papers, and I have to admit as secondary students, right, we did not have a lot of background, and hence meant that the amount of things that we learned had severe limit to it, but we still learned a lot about the technical and mechanical aspects of Auxetic materials, and I think we actually push our boundaries, push our limits to the very maximum to learn as much as we could. So with all this research in mind, right, we could actually maximize our efficiency because our designs, we know what we are doing, hence making sure that our designs are more likely to be successful. Hence, as you can see, research has been a very important learning point. So this is actually our soft-core learning points. Our technical learning points have all been taken care of in our video, and I hope that judges as well as students who might be looking at this video, you guys will actually understand that the entire learning process that we undertook and the numerous learning points that we encountered. Judges, and I hope you have a great day.